Hi, and welcome to my channel, JaberTime, where I do math videos for all levels, from algebra to calculus and differential equations, simplified with examples. I'm also adding videos on apps and programs to help students and teachers alike, enhancing the learning and teaching online. If you're new here, welcome, and consider subscribing and hit that like button so that I know that you enjoyed this video. And also let me know in the comments below if you have any questions. I do upload a video or two every week, and I'm so excited about converting all my math notes from teaching over 25 years into simplified YouTube videos with examples. Once again, thank you for being here and hope to see you again and again. Alright, let's get into it. Infinite limits. This is the second part 2 for limits. I do have another video that I started last week for Calculus 1. You might want to check that. I'll list it in the description below. So we have here just like a quick introduction about limits and basic functions that you need to know. Y equals 1 over x. As you could see, it's two pieces, one in the first quadrant and one in the second quadrant, or in the third quadrant, sorry. What happens is, as you get close to 0 from the right side, right here, the graph takes you up, all the way up. So 1 over x becomes hard to follow with a magnitude of greater numbers. 1 over 0.01, for example, is 1 over 100, which is 100. So it gets large and large, so we say it gets to infinity. If you approach 0 from the left side, you're gonna have negative numbers. Same thing, like negative 0.01 will be negative 100. So from the left side of 0, you're gonna go down to negative infinity. Since from the right side of 0 you're going to infinity, and from the left side of 0 you're going to negative infinity, we say that the limit does not exist. I'm writing the notes, as you could see before I record the video. You could slow down, pause, and look at the notes, but as you could see, I'm trying to go fast a little bit to save you some time. I don't end up making a video of like an hour, 2 hours. There is so much about limits. Last video was 41 minutes and I called it part 1. So if you see me going fast, it's just like general quick notes that I want to present and show you, which is going to help us for the coming examples. Alright, now since we're looking at also infinity, I'm gonna consider going always to all the way to infinity. The limit of 1 over x as x goes to infinity is 0. You're approaching the x-axis. How about if you go all the way to the left? It's gonna be also 0. This title right here, infinite limits, is your answers will be infinity and negative infinity. But I added these since we're still on the topic of limits. Alright, that's for the coming section, which is end behavior. That's what they call it. Alright, here's another example that students should be aware of. 1 over x to the second. It's not like the first one. What happens is it's pretty much the same behavior, except when you are on the left and you plug in negative numbers, you're not gonna get the negative numbers, so you're not gonna be in the third quadrant. 1 over x to the second is gonna be slowing down faster and going up faster, but it's not gonna be negative. So instead of having it down here, it flips, if you wanna call it that way, to the top. So both pieces are on top now. That's the main difference. Now, if you approach 0 from the right, it's positive infinity. If you approach 0 from the left, it's positive infinity. So we say that the limit exists this time and we call it infinity. Since, as I mentioned, we're talking about infinity and limits, let's go all the way to the right. Going to infinity, approaching values all the way to the right, you're gonna get close to the x-axis, so the answer is 0. Same thing, going all the way to the left to negative infinity, your values will get smaller and smaller, you're gonna go to 0. Here's a quick summary of some graphs. This is 1 over x to the second, the one that we're looking at. If you have a negative 1 over x to the second, the only difference is your values now are negatives, which is a reflection about the x-axis, as you could see. This is good to know. Same thing, I graph things by hand. I don't want to make it perfect. I think it looks good by hand. It's not exact. This should be exactly like this, but you know, it's by hand. I use colors and I like it to be outstanding and visible to see the behavior of the graph. What happens here compared to this one is I'm inserting right here negative 4. We call it in math shifting the graph, this parent graph, to the right 4 units. Here you cannot plug in 0, which is the 0 of the denominator, which is a vertical asymptote, but I'm not graphing it here. I'm saving those for later. And it's kind of hard to graph a vertical asymptote dashed line like this one right here on top of the y-axis. But the 0 that forces the denominator to be 0 is 0. The number that forces, we call it 0, the denominator here to be 0 is 4. 4 minus 4 is 0, which we're not allowed to have it there. 1 over 0 is undefined. So 4 acts here as x equals 4, which is a vertical asymptote. Alright? Here's a shift of the first graph that I started with to the right 5 units. So at 5, which is what forces the denominator to be 0, we have a vertical asymptote. Alright? Going all the way to the right, x approaches infinity is 0. It's getting close to the x-axis. Going all the way to the left, it's approaching the x-axis from the bottom side, which is still 0. So x equals 5 is called a vertical asymptote, this one right here. And let's move on and take another graph. I did not write here in the notes that this x-axis would be called also a horizontal asymptote. Alright? Now, why this graph behaves this way? You might think that I'm shifting the graph to the left 3 units, but no. It has to be the 3 next to x, not x to the second. Let me take you back and I'll show you what do I mean. See this right here? 4 is next to x and the whole thing is squared. So that's what's called shifting to the right and left. Going back here, notice the denominator is always positive, x to the second plus 3, which forces the whole value to be always positive. That's why I'm in the first and second quadrant. Nothing forces this to be 0, so I'm not touching the x-axis. Alright? Now, it's a behavior of a fraction that the numerator is fixed to be 1. And if we assume x equals 0, I get 1 over 0 plus 3, which is 1/3. That's why it's 1/3 right here. Okay? Now what happens if you go right or if you go left? Why the graph says your numbers are getting smaller and smaller and smaller? Well, Of course, if you go to the right or left, it doesn't matter. You're gonna square the number, so positive or negative, you're gonna square it. For example, 5 to the second is 25 plus 3 is 28. Negative 5 to the second is 25 plus 3, which is 28. So both sides symmetrical is 1 over 28, which is a small number. That's why it gets smaller and smaller and smaller. So the largest number or value for the function will be when you plug in 0 right in the middle. So let's look at the limits. As you go to infinity to the right, you're gonna get to 0. As you go to the left, you're gonna get to 0. And we call the x-axis horizontal asymptote. Let's look at another example. This example talks about x over x to the second minus 1, the whole thing being squared in the denominator. They want the limit as x approaches negative 1 and the limit as x approaches 1. Most of the first examples I'm looking at the graphs to discuss the behavior and support the answers, but there is also other methods which you're gonna see. So here's the graph. Why is that? Why we have a vertical asymptote at 1 and we have a vertical asymptote at negative 1? We'll see. We have a vertical asymptote here at negative 1 and we have at x equals 1 also we have a vertical asymptote. Look at this right here. This is our function. If you factor inside x squared minus 1, which is a difference between two squares, I get inside, let's call it brackets now, keep the second degree out, x minus 1 and x plus 1. Now those are zeros of the denominator, which means I cannot use them. They are out of my domain. My domain is all real numbers except 1 and negative 1. What forces this to be 0 is 1, and what forces this to be 0 is negative 1. Whenever you have zeros like these guys, that forces the denominator to be 0, you have vertical asymptotes. Now the behavior why this goes up, not down, is approaching it and plugging some numbers, which I have some examples for you. But at least you know why we have vertical asymptotes. Now, here's limit of my function as x approaches negative 1. It's gonna go down to negative infinity as the graph shows. Limit the same function as you approach 1 is positive infinity. So let's take it to the left. Limit of our function as x approaches negative infinity, going all the way to the left, we're getting close to the x-axis, so that's going to be 0. And going all the way to the right, that's also going to be 0. And here's another example. I'm just slowing down so you could see everything. It's just like understanding graphs and behavior close to vertical asymptotes and infinity and negative infinity values of x-axis. Now, before I start, if you notice, we have denominator factored pretty much and a numerator. Well, they don't communicate, which is kind of nice for now. We have a 0 here at x equals 3. We have a 0 here coming from this factor, which is x equals 1. So what do you expect? What do you think the graph is going to look like? Where do we have vertical asymptotes? We have a vertical asymptote at 1 and a vertical asymptote at 3. Notice that through 2 it crosses the x-axis at 2, so the value of the function is 0 when x equals 2. If you plug in 2 here on top, you will have 2 minus 2, which is 0. 0 over anything, I don't have to worry about these numbers, they're not going to be 0. 0 over a number is 0. So those are critical 3 numbers that we need to know. So the limit approaching 3 from the left, the graph shows from the left. The graph shows you're coming this way from the left of 3, so you're going down to negative infinity. Approaching 3 from the right, you're gonna go up, so it's positive infinity. They're different from left and right of the number is 3, so we say the limit does not exist. Now this is just focusing on the graph. I need to show you more details, so let's pick this number or the first part. I want to go over the second part, and so on. In one example, I have more examples to show you. So let's take the first one. Here's the first part. What is the limit of f of x as x approaches 3 from the left? We know the answer, negative infinity, but let's analyze and see why. Our function is x minus 2 over x minus 1 to the second over multiplied by x minus 3. Now, approaching 3 from the left, like 2.9, so this is going to approach 1, and it's going to be positive. This is always going to be positive because it's a second degree. Now this part right here will approach to 0 because you're approaching 3 here and you're subtracting 3, so you're going to approach 0. But you need to keep in mind that your numbers are negative. Let me help you understand that. Think 2.9 minus 3 is negative 0.1, 2.05 minus 3 is negative 0.95, 2.999 minus 3 equals negative 0.001. So you are approaching 0, but your numbers are negative. Positive, positive, negative. Not only that, there is more into it. If the denominator is getting to 0, the fraction is getting to infinity. So we have kind of like a plus and a minus, which we discussed right here. But we also have the idea that we have a fraction with numbers, except one piece down here is taking me to 0. So the whole thing is going to approach infinity. But I need to keep in mind that my answer should be negative. So it's negative infinity. I hope that this is clear to you. It's just little pieces here and there. And in case if you want to take the limit as x approaches 1, we're going to have infinity. That's just to add to it. I have 3 and I have 1. 2 is not something that we worry about. And let's take another example. 2 minus 5x over x minus 3. We're going to approach 3 from left and right, and we'll see if the limit does exist or not. Now, on top 2 minus 5x, if you approach 3, you're going to approach 2 minus 5 times 3, which is negative 13. Down here, you're approaching 3 from the right, so you can't use 2.9 like in the last example. You're going to use something like 3.01 and 3.001 and so on. So 3.01 minus 3 is going to be positive. So you're going to approach 0 in the denominator, but it's going to be positive. So numerator is negative 13 or approaching negative 13. Denominator is positive, so you have negative over positive, but the denominator is getting close to 0. So our limit is negative infinity. Negative over positive is negative. The denominator is getting close to 0, so the answer is negative infinity. Using or approaching 3 from the left is going to make a difference. The top part we said negative 13, the bottom side is going to be negative this time. Okay? Imagine I have like negative 2.9. 2.9. Approaching 3 from the left something like 2.9, not 3.01. Minus 3 is going to be negative. So you have negative over negative, which is positive, and this is approaching 0. So the answer should be positive infinity. Therefore, the limit does not exist. Here's another example. This is a very interesting example, and I'm taking my time over it, which I took as an image for my thumbnail for this video. So if you notice that graph in the thumbnail, it's from this graph of this example, which has enough in it. So I'll go through it, and then you will see some slides coming summarizing it. So if you wanna follow me and stop the video, look at the notes when I combine them in one slide, you're more than welcome to do that. Let's move on. Here's the graph. It's x squared minus 4x plus 3 over x to the second minus 1. If you notice the graph, there is a few things happening, and we're gonna discuss it, as I said, and support everything in it. So here's my fraction, and if I factor the bottom side, it's a difference between two squares, so it's going to be x minus 1 and x plus 1. The top part is going to be x times x and 3 times 1, and I need to end up with negative 4, so I'll have to go x minus 1 times x minus 3. But notice what happens here. There is a few things happening. First of all, this cancels. Also, we have zeros for the denominator. This gives me x equals 1 as a 0 for the denominator. This gives me x equals negative 1. Those are zeros for the denominator. This 0 got cancelled by this. That's when x equals 1. When x equals 1, this behavior, it's a hole in the graph. This 0 did not get cancelled. Anything of this nature, which is x plus 1 equals 0, subtract 1 from both sides, so what forces this to be 0 is x equals negative 1. That is a vertical asymptote. One more time. This behavior gives you a hole in the graph. This behavior gives you a vertical asymptote. Okay, so my function simplifies to this, but I have to write this down, provided that x cannot equal to 1, because I could divide top and bottom side by x minus 1 as long as x does not equal to 1, which means as long as x minus 1 is not 0. So with that in mind, we say that at x equals 1 we have a hole in the graph. Limit f of x as x approaches 1 is just negative 1. You can just plug it in here direct. You don't have to write 1.001 and so on, because we got rid of this out of our way, acting like it's not there. So it's plug in 1 minus 3 over 1 plus 1, which is negative 2 over 2, and that is negative 1. Approaching negative 1 from the left, right here, from the left, we have infinity. Approaching negative 1 from the right, so we're gonna get down here, that's gonna be negative infinity. That says that the limit, or at x equals negative 1, we are approaching infinity and negative infinity. It doesn't have to be the same up or down. They could be of this nature. We have a vertical asymptote. As I mentioned earlier, there is a hole, there's a vertical asymptote, and that is the details why this is happening. If you need more details, why this is happening. And as you can see, I skipped some steps in writing all the details, like positive and negative, like negative 4 and 0. Go through this and you should be fine. I just don't want to read the whole thing, and I have more important stuff to cover. For example, the coming slide, and you'll see why. And I have more examples, of course. That's one reason why I'm not reading the previous slide, I'm showing you this slide. So this is a summary of this whole problem without writing too much. You see the graph is fully detailed, and I'm even adding more to it. Here's a hole in the graph at x equals 1. We have a vertical asymptote at x equals negative 1. I added also a horizontal asymptote at y equals 1. Where's that coming from? If you look at the graph or the equation, the original equation is this right here, and I'm adding the leading coefficients for the leading terms, 1 and 1, in a blue color to show that they are equivalent. Since we have the same power, a second degree function over a second degree function, so m equals n, same degree. The limit of this f of x as x approaches positive or negative infinity, in this case, is 1, which is actually the leading coefficient a sub m, that's this one here, over the leading coefficient b sub n, which is this one down here, and that is a horizontal asymptote at y equals 1. Just make sure that when you mention horizontal asymptote, it's y equals, not x equal. And this was covered also. That is the idea of the vertical asymptote and the hole. This is vertical asymptote behavior, and this is a hole in the graph. Zeros of the denominators are one coming from here and one coming from here. The one cancels, is a hole in the graph. Okay, I think that's enough for this problem, because I have more problems and more slides to go. I'm looking at the time, it's about 25 minutes so far. Here's an example. I have the example, and I have the graph, and I have the answers, as you could see. Approaching negative 1 is taking you down to negative infinity. Approaching 3 is infinity. So we have our function right here. As x approaches negative 1, this is more detail why this is happening. Top part is going to be negative. The lower part, if you factor it inside the brackets, is two pieces. X plus 1 approaches 0 because x is approaching negative 1. X minus 3 is just a number, like negative 1 minus 3. But the whole thing is going to end up positive. Approaching 0 times a 4 is approaching 0, but positive. Negative over positive is negative. Denominator is approaching 0. So we have, as approaching negative 1, you're going to go down to negative infinity. Negative over positive is negative, negative infinity. And because of the 0 down here, it's all the way down to negative infinity. When you approach 3, the graph shows it's positive infinity. More details. This is positive, of course, because of the second degree. This is going to take me to 0. So positive over positive, but the denominator is taking me to 0, positive infinity. Now, looking at this one more time, the domain is all real numbers except -1 and +3. What causes the denominator to be 0? And they don't cancel. So we have vertical asymptotes at -1, at 3. As you could see, we don't have holes in the graph. None of these factors cancels. So just to support the concept of the vertical asymptotes also. This is a quick example. If you have a fraction or rational function, the top part is fixed. Doesn't have to be 1 all the time. It's 100. G of x, the denominator, is going to 0, but they're telling you that g of x is negative. It's approaching 0, but from the left. Okay? Positive over negative is negative. 100, which is fixed, over something that's taking you to 0, is an infinity. Negative infinity is our answer. 1 over x minus 2. This is similar to my introduction, 1 over x, but shifted to the right 2 units. They want you to see approaching 2 from right, approaching 2 from left, and if they both agree, to see if the limit is the same. This is another way, instead of looking at the graph. The top part is fixed. The bottom side is approaching 0, but it's positive because you're approaching 2 from the right, like 2.1 minus 2. That's a positive. So the answer is infinity. Approaching 2 from the left, you're going to have 1.9 minus 2. That's going to end up negative. So we have a negative down here, we have a positive on top, which is fixed, and that's going to be negative infinity. Here's a support for this to say that the limit does not exist, because it's going one side to positive infinity, the other side to negative infinity. We say the limit does not exist. And of course we have a vertical asymptote at x equals 2, because this did not get cancelled. So that's a quick short answers. Infinity, negative infinity, and does not exist. Another example. Also nothing cancels, which is good to know. This will cause a vertical asymptote at 3. This will cause a 0 for the function, which means the graph is going to cross the x-axis or passes through the x-axis at 1 and also at 2. Okay, this is positive, approaching 3 from the right. This is positive. This is positive, 3 minus 1, 3 minus 2. Approaching 0, but positive. Infinity. More. Same concept, same idea like before. So we have infinity, negative infinity does not exist. Now this is a little bit different example. I mean, it's not high level, but why not? Let's go over it quick. Notice that I have only one term right here, and I have x's all over the place. I don't have a constant, so a good way is factor out x squared from top to cancel it with the bottom side, as you could see. So that cancels, and I'll end up with x minus 5. I should write next to it that x in the red cannot equal to 0. I have it here as a comment. So my graph, if you graph it, try to graph it on the calculator, you will see that you're not going to be seeing sometimes the holes in the graph because the settings of the graph. If you need help with the graphing calculator, you need to change the settings. Ask me in the comments below if you need any help, if you have any math questions of this nature, and I'll get back to you. In the meantime, I know this is a line, x minus 5, with a slope of 1 and a y-intercept of -5, but cannot cross the will be a hole in the graph at x equals 0, because you're approaching 0 but you cannot be at 0. You cannot be at 0. Okay? So the limit is -5. I think that should do it. I'm trying my best not to have everything in one lecture. It just doesn't work this way. Part 1 was about 41 minutes. This one I'm assuming it's about 35 minutes. So if I could keep my videos 30 minutes, 20 minutes, 15 minutes, or even less by targeting 2 main topics, I think that will help. Let me know in the comments below if my videos like this one or the previous one, which is 41 minutes, are considered lengthy. And if you think I should make them always about 15 minutes, let me know. I started the YouTube channel just like 2-3 months ago, and I'm doing my best to, as I said in the beginning, to put everything I know in slides, converting all my notes or my knowledge in math into YouTube videos. Okay, just let me know, guys, and I hope that you do like my notes. I'm trying to get to the point of it. Instead of reading a text, I'm trying to, through slides, show you exactly the keywords. Like for this example, for this video, vertical asymptotes, horizontal asymptotes, a hole in the graph, and why do they happen, starting with basic knowledge of graphs, like 1/x and 1/x a second. So that should do it for this video. I do want to thank you for watching. If you are up to this moment, that means you stayed with me till the whole time. I do really appreciate it. I hope that this video was helpful. Hit the like button if you do like it. That will help me a lot and will let me know that I'm doing a good job, so I could keep going. And as I said, I've been teaching for many years, and I would like to convert all my notes to YouTube videos. Comment below if you have any comment, please, and I will do my best to respond back to you. If you like this video, hit the bell icon to be notified when I upload new ones. There's videos every week. That's my plan and that's my commitment. Until next time, peace, JaberTime. Thank you again.